If f is a positive, continuous, and decreasing function for which x is greater than or equal to 1, and a sub n can be written as f of n, then the infinite series, the sum from 1 to infinity of a sub n, and the integral from 1 to infinity of f of x dx will either both converge or both diverge. That's called the integral test theorem. Using this as an example, suppose you're asked to decide whether or not this series, infinite series, converges or diverges. If we rewrite the a sub n part as a function of x, we write that as x over x squared plus 1. Using a graphing utility, or just plug and chug numbers like 1, 2, 3, 4, and so on, you will see that for positive integers, x is positive, it's continuous, and you can verify this, like put this function into your graphing calculator and graph it just to check. But anyway, this function is positive, continuous, and the y values decrease the whole time. Therefore, we can apply integral test and take the integral of this function from 1 to infinity, and we discussed these back in the improper integral homework section. This denominator has a derivative of 2x, so what I did was I gave the numerator a 2, but I balanced it back out with a 1/2. So the antiderivative is going to be 1/2 natural log of our denominator. Since x squared plus 1 is always positive, I use parentheses instead of absolute value. We have infinity and 1 as our upper and lower limits. Natural log of a really huge x values. Normally in the improper integrals we would write that as limit as b goes to infinity, and I would write that with the letter b. But after you've practiced those long enough, you can kind of intuitively plug an infinity in. Infinity squared plus 1 is infinity. Natural log of infinity is also infinity. Plugging a 1 in is natural log of 2, which is finite, but that infinity rules over all of it. And so, because that's not a finite value, the integral and consequently the infinite series diverge. A second example would be the sum from 1 to infinity of 1 over n squared plus 1. Let's write a sub n as a function of x. That'll be 1 over x squared plus 1. Again, if you want to use a graphing utility, feel free. This function is always positive. It's continuous because no real number creates a zero denominator, and it's decreasing. The larger the x's, the smaller the fraction's value. Using integral tests, we're going to integrate from 1 to infinity of 1 over x squared plus 1. This fraction has an antiderivative of arctangent. In the bottom right, I re-sketched the graph of arctangent just as a reminder. We've looked at this graph several times. As x gets really large, there's a horizontal asymptote at pi over 2. So arctangent of infinity is pi over 2, minus arctangent of 1, which is pi over 4. That has a difference of pi over 4. That's a finite number, so that tells us that this infinite series converges. If the integral has a finite value, the series, infinite series that it represents, is convergent. If an infinite series diverges, then that integral will not have a finite value. For p series, you have an infinite series from 1 to infinity of 1 over n to the p, which if you started expanding that, increasing your n values, that's 1 over 1 to the p, plus 1 over 2 to the p, plus 1 over 3 to the p, and so on. This infinite series will converge as long as the p-value, or the power, is greater than 1. It diverges for p greater than 1 but less than or equal to positive 1. If p is exactly 1, then you have what's called a harmonic series, and it is divergent. Sometimes your infinite series is written plainly, like this one. The series, we have the sum from 1 to infinity of 1 over n cubed. Our p-value is 3. That's larger than 1, so that's a convergent p-series. Sometimes the series is written out longhand, and you have to figure out what its nth term is. Well, the second term has a 2 and a square root of 2. The third term has a 3 and a square root of 3. Fourth term, 4, square root of 4. So the pattern is 1 over n square root of n. The sum from 1 to infinity of 1 over n times the square root of n. This n has a positive 1 for a power. This n can be written as 1/2. Since these are multiplied, 1 plus 1/2 is 3/2. That p-value is 3/2. That's greater than 1, so this infinite series, which happens to be a p-series, converges also. The reason a harmonic series, when n is 1, doesn't converge, it's divergent, is, let me pull up some ink here. If you were to look at the infinite series from 1 to infinity of just 1 over n to the first, you could apply the integral test write 1 over n as a function of x. This antiderivative, I'm going to go ahead and do it properly with the limit as b goes to infinity. The antiderivative of 1 over x is ln of x. Since we're going from 1 to infinity, I'm just using parentheses instead of absolute value. And then we evaluate b, that's ln of b. Minus ln of 1, which we know that ln of 1 goes to 0, so I can cross that out. That goes to 0. And then as b goes to infinity, this does too. Keep in mind 1 over x is positive, continuous. From 1 to infinity, it's continuous. Now, it's not continuous when x equals 0, but that's not part of the original sum or this integral. So you get away with it there. Positive, continuous, and decreasing. As x gets larger, the fraction gets smaller. I hope this helps. Let me know if there's anything you need. Reach out by email or phone. Ask in class. I'll do my best to help you out.